All right. Our next lecture is by Professor Silviu Pufu from Princeton. His last lecture about gauge theories at strong coupling and IDS CFT.
Okay. So just to recap where we were. So we've been discussing the duality between n equal 4 super Yang-Mills in 4 dimensions with gauge group SUN. And type 2B string theory on ADS 5 times S5. When n, the rank of the gauge group, is much bigger than 1, then the theory in the bulk becomes classical. The loops are suppressed. And when the Tuff coupling, G Yang-Mills squared n, is much bigger than 1, then the theory in the bulk is a 2-derivative theory. It's a 2-derivative supergravity, becomes a 2-derivative supergravity theory. And that's because when lambda is much bigger than 1, the higher derivative corrections are suppressed in powers of 1 over lambda. So what does the bulk action look like? Well, so at leading order, there's the Einstein-Hilbert term plus its supersymmetric completion. It comes multiplied by 1 over the Newton constant in 10 dimensions. So this is a theory in 10 dimensions, of which ADS 5 times S5 is a solution of the classical equations of motion. But in addition to this, there are higher derivative corrections. The first higher derivative correction has 8 derivatives, and it's a specific contraction of 4 Riemann tensors plus its supersymmetric completion. Because this has 8 derivatives and that has 2 derivatives, this has to be multiplied by the string length to the 6th power. Then the next term has 10 more derivatives, is 12 total. Sorry, 12 total, 8 from here and 4 from there. So it's 4 derivatives and 4 Riemann tensors, and the next term is 6 derivatives and 4 Riemann tensors, and then it keeps going. This is all nice. However, so each of these terms comes with its own supersymmetric completion. This is all nice. However, the full supersymmetric completion of the higher derivative terms, even the first one, the Riemann to the 4th, is not completely known. So this expression is in some ways schematic if we don't actually know all the terms, but we believe that there's a unique supersymmetric completion. Okay, I wrote down the dictionary here. So lambda is the Tuff coupling, G Yang-Mills squared n is the 4th power of the radius of ADS divided by the string length to the 4th power, and the term that appeared, the factor that appears in front of the action, 1 over the Newton constant in 10 dimensions, is proportional to n squared. And this kind of action, as well as the rule for computing correlation functions of operators, of local operators in the boundary theory, which is that an operator on the boundary should be identified with the limit of a corresponding bulk field. So this is for single trace operators. They have this property. So we discussed last time, we drew some diagrams that showed that the 4-point function of some operator on the boundary takes this schematic form where I just wrote down the powers of n and the powers of lambda. Of course, each term here is a full function of the positions of the 4 operator insertions. So the first term goes like n to the 4th and lambda to the 0. That's just a disconnected contribution. So products of 2-point functions. And the first connected contribution, so with the normalization where the 2-point function goes like n squared, then this is n to the 4th. And then the first connected contribution to the 4-point correlator goes like n squared, and there's various powers of 1 over lambda. The leading term that comes from just exchange diagrams using supergravity vertices goes like lambda to the 0. The next term goes like 1 over lambda to the 3/2, and this comes from contact interactions with an r to the 4 vertex. The next term, like 1 over lambda to the 5/2, contact interaction with d to the 4 r to the 4 vertex, and 1 over lambda cubed. It's a contact interaction with d to the 6 r to the 4 vertex. So everything that multiplies n squared, these are all just tree-level diagrams, no loops, because the loops are suppressed in powers of 1 over n. And then if we go to the next order in 1 over n, which would be n to the 0, then we have various contributions that are also come from loops. So that's the roughly what we expect a 4-point function to look like when expanded at large n and large lambda. Good. So now you might ask, okay, if this is schematic, because we sort of know this is what it looks like, but we don't know all the terms, and sort of that implies that, how do we actually know that that expansion has that form? Do we have any checks on it? And what I want to show you today is to show you one check on this kind of expansion. Good. Yes.
So in a onward n expansion, we
Yeah.
see that for everywhere
Yeah.
the leading lambda exponent is positive.
Yeah.
Does this and it's growing with powers of 1 over n.
Yeah.
Does this feature persist at higher orders? And,
It persists at high orders, and that's just because the first few orders in 1 over lambda, the ones with positive powers, actually come also from contact diagrams. They're corrections to these contact diagrams, to the r to the 4 vertex. There's a correction that produces something that goes like lambda to the 1/2. So this is what happens for all the ones with positive power. So the loops actually start at lambda to the 0 from here on. Yeah.
to make this perturbation very well defined, we also have to ensure that some lambda over n has to be smaller. Have to,
Yeah. So this
might be some.
good. So this is written down assuming that n goes to infinity first, and lambda is kept fixed, and then we expand later on in 1 over lambda. We could take other limits, but this is the limit in which this is written down. Yes.
Why are there no like R squared there?
There's 10-dimensional supersymmetry, and that prohibits them. Yeah. So the first correction is Riemann to the 4. Yeah. 8 derivatives.
What are the dots?
The supersymmetric completion. So in 10 dimensions we have graviton, but we have other fields. So there's also terms involving the other fields. So that's what the dots mean. So there's like a dilaton, there's like fermions, there's various gauge potentials. Any other questions? Okay, so I wanted to show you this expansion in the simplest case that I can. So we have to choose an operator O for which to look at the 4-point function. One thing I mentioned last time, I didn't prove it, is that in order to have a finite limit in that expression, when we take a bulk field to the boundary, that imposes the condition that the mass of the bulk field squared is delta times delta minus 4 divided by L squared. So the masses are in units of 1 over the radius of ADS. This is true. Yeah, this is true only for scalar operator. Yes, if phi is a scalar. Otherwise, it gets modified, but it doesn't get. It gets modified only a little bit. Okay. So what kind of operators do we have in n equal 4 super Yang Mills? So we have operators. So these are all single trace operators that I want to discuss. So we could have operators where the scaling dimension delta, as we take n to infinity and lambda to infinity, stays a finite number. So it goes like n to the 0 and lambda to the 0 at large n and large lambda. And these correspond to fields in ADS5 that are obtained from the 10-dimensional fields after expanding them in harmonics, in spherical harmonics on the S5. So 10D fields reduced on S5. That's what I mean by reduced on S5. We just expand them in harmonics. We have an infinite number of them. And the mass, because of this, the mass that they acquire in ADS would be proportional to 1 over the radius of the S5. And the radius of the S5 is the same as the radius of ADS5. So it's 1 over L. And that's consistent with the fact that in this formula, delta is going to stay fixed as we take n to infinity and lambda to infinity. So there's some examples. Or maybe I can raise the board. Some examples. Okay, success. So examples. So for example, if you recall the field content of n equal 4 spectrals, there's a gauge field, there are some scalars and some fermions. If we take trace of f mu nu, that would be an example of such an operator. This operator has dimension 4. It belongs to a protected superconformal multiplet, so its dimension is actually doesn't depend on what n we have and what lambda. And because delta equals 4, we get that the scalar operator, we get that this would correspond to a massless field in ADS. Another example would be trace of phi I. So let's call the n equal 4 scalars, let's call them phi as last time. So phi I, phi j minus 1/6 delta ij, phi k. And this again belongs to, one can work out the representation theory, the superconformal representation theory, and this belongs to a protected multiplet. It's the same multiplet that trace f mu nu squared belongs to. And this has a protected dimension that we can figure out. If it's protected, we can figure out what it is from weak coupling, where a scalar field in 4 dimensions has dimension 1. So this is a bilinear in that, so this should have dimension 2. So this corresponds to a scalar in ADS of mass squared minus 2 over L squared. In ADS, slightly negative masses are allowed, but not too negative. Just as another example, we can have trace phi I1, phi I2, and so on up to phi ik for some number of them. And then we have to subtract in order to make an operator with the properties I'm going to say. We have to subtract the SO6 traces. And this will have delta equals k. So the mass squared would be k times k minus 4 over L squared. Not too negative. So the masses that are bigger than, if I remember it correctly, it's minus d squared over 4L squared. It's called a BF bound. Yes. Where d plus 1 is the dimension of ADS. I hope I got it right. Anybody remembers it? Yeah. It should be the value that we get when delta is d over 2. So I think that delta times delta minus d. This is correct. Okay. So in the case of ADS 5 times S5, all single trace operators actually belong to all single trace operators with dimensions that don't grow as we go to large n and large lambda belong to protected multiplets. All protected multiplets. Yes. The trace outside? Or the trace outside is over the color indices, yes. Which are not written down. The phi's are matrices, they're n by n matrices. We multiply the matrices and then take the trace of those matrices.
But then how should I understand this? Is it a scalar operator?
Yeah, it's a scalar operator. So n equal 4 super I mills has the gauge field, has some fermions, and it has 6 scalars, phi I. So I goes from 1 to 6. And these scalars are n by n matrices. So we have to, if we specify what the indices are, we have to still, in order to construct gauge invariant operators, contract all the SUN indices. They're in the adjoint representation, yes. If we make a list of them, there's n squared minus 1 of them, but we can represent them as n by n traceless symmetric, traceless Hermitian matrices. Okay, good. And all these operators, so all these operators must have spins of most equal to 2, because otherwise they cannot be constructed from supergravity modes. So that's the should be a consistency check of ADS CFT, that there are no operators with higher spin whose dimensions that are single trace and whose dimensions stay finite as we take n to infinity and lambda to infinity. What does it mean to have a negative mass squared? Well, m squared is just a parameter that appears in the action for scalar field in ADS. So it could be a little negative. Yeah. Okay. So in addition to these, there are also other kinds of operators. I'm not going to say much about them, but they're, for example, operators for which delta still stays like n to the 0 as we take n large and lambda large, but go like lambda to some positive power. Those would not be constructed from these fields. They could be dual to, for example, excited string states. So these fields that appear in this action came, in string theory, they came only from the lightest string modes, which were massless in 10 dimensions. But there are also massive string excitations, and those would correspond to operators whose scaling dimensions grow. And as an example of that, the operator trace phi I is an example. And for this kind of operator, the dimension goes like lambda to the 1/4 at large lambda. This is a Konishi operator. Yes. And in addition, there are also operators for which delta goes like n to some positive power, maybe lambda to some positive power. I'm not going to talk about it. So for the rest of today, we're going to focus on the simplest one. And I'll call that operator Sij. So this would be trace phi I, phi j, minus 1/6 delta ij, phi k, phi k. That's the lowest dimension operator one has, is dimension 2. Okay. And how am I going to get an expansion that looks like that? Well, by computing something in the field theory. The field theory is strongly coupled. So our best hope of computing something using the field theory is some quantity that's protected by supersymmetry that could be computed using supersymmetric localization, which will give some matrix model, like the matrix model that I showed you last time for the circular Wilson loop. So it would be a generalization of that matrix model. So I want to explain roughly what that generalization is. So exact results for the 4-point function of this S operator from supersymmetric localization. So the rough idea of supersymmetric localization is this. Just so that I'm not going to go through all the details, complicated subject, but I just want to give you a flavor of where this will come from. So if I have a supersymmetric quantum field theory with a Lagrangian, and we put it on a manifold M, it's supersymmetric, so it should be invariant under some supercharges. And in particular, it would be some supercharged Q. So we choose a Q. And if we can find some fermionic operator psi such that the anti-commutator of Q and psi, if psi is fermionic, then the anti-commutator of Q and psi will have will be bosonic. So if this is positive definite, and if Q, this anti-commutator, so and this anti-commutator is invariant, is itself supersymmetric, so is invariant under the supercharge. Then the following statement holds. Suppose we're interested in computing the partition function of this theory on this manifold. A partition function is an integral of e to the minus the action in Euclidean signature. Suppose this is what we want to compute. Well, we can change it, change the exponent by adding to it this commutator of Q and psi with some coefficient t. And one can show, because this is an anti-commutator of Q with something, and the theory preserves supersymmetry, one can show that this partition function doesn't depend on the parameter t that we put in front. So we can have, if we're interested in computing the answer for t equals 0, but we're guaranteed, because of supersymmetry, to get the same answer regardless of what t we choose. So then the trick of supersymmetric localization, so this is independent of t. So then the trick is to take t to be very large. And if we take t to be very large, then the contributions to the integral, to the path integral, will come from places where the term multiplying t, this anti-commutator of Q and psi, is the smallest possible. But if it's positive definite, the smallest possible is 0. So the contribution to this integral will come from places where this anti-commutator vanishes. So I'm going to write that down. So take t to infinity, and then z localizes to field configurations obeying q psi equals 0. So when t is very large, we can, because we have a very large number multiplying something, we can use a saddle point approximation. So saddle point at large t implies that the partition function becomes now an integral. I probably need more room, so let me this. So the saddle point at large t implies that the partition function is approximately a large t, but of course approximately means exact because the answer is independent of t. So it's equal to an integral over field configuration x with the property that q psi is equal to 0 for whatever operator psi we chose. So this is dx e to the minus x. So instead of having an infinite dimensional path integral, instead of having a path integral, we have a restricted integral where x is restricted to the solutions of these equations, whatever those solutions are. And then from this term, we expand it to quadratic order. If it's multiplied by something really big, we can expand it to quadratic order and compute the one loop determinant. So this would be times the one loop determinant of fluctuations around these saddle points. Ideally, what should happen? So ideally, our best case scenario, if we were to solve these equations, q psi is equal to 0, we'll find only a finite dimensional space of solutions. If we have a finite dimensional space of solutions, that's the same thing as saying that we're integrating over just matrices. So this is how to get a matrix model. Show you how this happens in unequal force triangles. Okay. So in this case, if this happens, if there's a finite dimensional space of solutions, then the theory. So for example, an example would be, the scalar fields are just constant on the manifold and all other fields vanish. Maybe these are the solutions to the equations q psi equals 0. So in this case, we just have to integrate only over the constant values of the scalar fields. That's the same as just doing a matrix integral. So Z would be a matrix model. Finite dimensional. Right.
So x equals constant to any constant.
Yes.
That's a class of solution.
That's right. So, but X is a matrix in our gauge theory. So we still have to integrate over those matrices. Yes. So if the matrices are constant matrices, then you still have to integrate over them. Yes.
So can you comment again why comment here?
Because otherwise, if we make this deformation of the partition function, If this has negative directions, then after we make the deformation, the answer would blow up. We want the answer to still be convergent. Okay. Yes. S of x. S of x will be S evaluated on the solutions of these equations q psi equals 0. So implicitly, it does depend on the choice of psi, because that could determine the solutions of this equation. That's correct. Yeah. That doesn't happen. Yes? Yes. Yeah. Yeah, the resulting integral is convergent. This term here, this expression is convergent.
This might be completely equivalent. No, computation is simpler just to look for some nilpotent supercharge and then look for its kernel, which is essentially psi, and solve that equation. And in a sense, so probably is it simpler to find solution to equation q psi equal to 0 than to this anti-commutator? But I guess it will be completely equivalent.
Yeah. So okay, the supercharge has to be chosen carefully. If the supercharge isn't chosen carefully, then the solution of these set of equations, q psi is equal to 0 for any side that we choose, could be too big. And then the answer would not, I mean, the method is still valid, it just won't be useful because it won't localize to a matrix model, localize to still a field theory. So that's a tricky thing about it. Okay, so this argument also works also with insertions as long as they're supersymmetric. So Q invariant insertions. So if we have some operators that are supersymmetric, we can still insert them in the path integral and compute their expectation values. And the same argument holds. So how did this work for n equal 4 Superang Mills? Let me write it down. Yes, sure. Yeah. The space of solutions. Sorry, so Q no longer acts on the space of solutions. Right. No, it's not guaranteed to be Q invariant. That's a requirement that one should impose, because usually Q doesn't square to 0. Yeah, good question. So what Princeton did, he did this. So he studied the n equal 4 Superang Mills theory. Instead of on R4, he studied it on a round 4 sphere. And then he applied this argument, constructed a Q, constructed a psi, and showed that what happens is that the solutions of this equation, Q psi equals 0, are that one of the scalars, let's just call it phi 6, is a constant. Let's call it M. Is a constant. And all other fields vanish. That's a solution of these equations. As long as we are away from the poles of the sphere. And if we are at the poles of the sphere, the allowed, so at the poles, the solutions of those equations are instantons, or supersymmetric instantons. At the north and the south poles of the sphere. And from this, he just computed that one loop determinant and found that the partition function on S4 is integral over these matrices M, e to the minus 8 pi squared over g n squared, trace M squared. So it's just a Gaussian matrix model. That's where that Gaussian matrix model came from. And the circular Wilson loop is an example of an operator that's still supersymmetric with respect to that supercharge that was used for localization. And this in the matrix model corresponds to an insertion of 1 over n times the trace of e to the 2 pi m, which is the matrix model that I showed you. Yes.
To calculate this quantity on S4, one would really need some formulation of background offset supergravity.
To place n equal 4 superagonals theory on S4? One doesn't really need that because it's a conformal field theory. That was the next comment I was going to make. So if it's a conformal field theory, we can define it on flat space on R4, but we can also do a transformation to any other conformally flat space, and S4 is an example of that. So note that we can have a CFT on R4. We can study it on R4, but we can also equivalently study it on S4 or on any other conformally flat space. There's explicit formulas for if we have a correlation function on R4, we can figure out what the correlation function is on S4 and the other way around. The one loop determinant factor is actually, in this case, it's sort of, the way the calculation goes, it's sort of hidden. I mean, the part of it that doesn't vanish, it's sort of hidden in the integral over the matrices. If we write down the integral over matrices as an integral over the eigenvalues, there's an extra Jacobian factor. And that you could think of that as coming from the one loop determinant. No, not topologically reduced. Well, there's a super algebra. So the theory on R4 is invariant on a superconformal algebra. There's a subalgebra of that superconformal algebra that's being preserved on S4. The only difference between the Lagrangian on S4 and the Lagrangian in flat space is a conformal mass term for the scalars. That's the only difference. And still preserve some superalgebra. Yes, with the yeah, that's right. So the supersymmetry parameters are killing spinners on S4. Yeah, that's right. But if you think about where those come from in flat space, those are linear combinations between the Poincare supercharges and superconformal charges. Okay, sure.
So will this be dual to ADS5? Because now the CFT is defined on S4.
So where was R4? R4 was at the boundary of ADS5. So where will S4 be? Well, in Euclidean signature will be at the boundary of ADS5. So it'd just be a different, if we want to describe the theory on S4 instead of R4, we should parameterize ADS5 differently such that the boundary looks like an S4 instead of R4.
Then you will be in Euclidean signature?
You'll be in Euclidean signature, yeah, that's right. Because S4 is a Euclidean manifold. I can write down the metric, but maybe I will write it down afterwards. Yeah. Okay, good. So in general, now how do we apply this to correlation functions? So in general, if we take a correlation function O of x1, O of x2, and so on, this will not be invariant under the supercharge. But there exist integrated correlators that are Q invariant. So what does it mean, integrated correlator? Well, the way to construct it is this. So suppose we still have a CFT and we deform the CFT by a parameter. So with a parameter, while preserving the supercharged Q, I need the boards higher. Okay. So what does it mean to form the CFT? Well, it means we start with a CFT action, and to it, we add a parameter times the integral of some operator, some local operator. So suppose we have its deformation, so CFT action plus some parameter, let's call it G, times D for X times some operator O of X, in such a way that we still preserve supersymmetry of the supercharged Q. Then, if we can do that, we can take a derivative with respect to the parameter G, and that derivative, and then evaluate it at G equals 0. So this would correspond to an insertion of minus the integral of this operator. So for example, if we take 1 over Z times the fourth derivative of Z with respect to G, and evaluate that at G equals 0, that's going to give us the 4-point function of, or the integral of a 4-point function of O. So it'd be integral d4x1, d4x2, d4x3, d4x4 times the 4-point function O of x1, O of x2, O of x3, O of x4. So even though the correlation function at separated points is not going to be invariant under G, if we take derivatives, if we deform the n equal 4 supraimil's theory by parameters, and then take derivatives with respect to those parameters and set them to 0, set the parameters to 0 after we take the derivative, we could get something that is supersymmetric.
Is it necessary for O to be exactly marginal?
No. O doesn't have to be exactly marginal. Okay. In fact, in the example I showed you, it won't be exactly marginal. And it's not important for the CFT to have to be on a conformal manifold. It's not important for it to have exactly marginal operators. So what are the parameters that we can use in n equal 4 supraimil's? Of course, is on S4. So we already know some parameters. There's of course G mills. It's a parameter. We could take derivative with respect to that. We don't have to set it to 0 afterwards. We could still take derivatives. There's also a theta angle. So in the action, we have 1 over 2 G mil squared times trace F mu near squared plus I theta over 8 pi squared in, well, it's an integral of this, integral of F wedge F, trace F wedge F. That's how theta appears. And it's convenient from them to form a complex combination, which is theta over 2 pi plus 4 pi I over G mil squared. And tau bar is the complex conjugate of this. So those are two parameters that we have, tau and tau bar, or G mills and theta. And another parameter that we have, we could introduce a mass that preserves, so mass parameter preserving some supersymmetry. One can have preserve n equal 2 supersymmetry. It's not that relevant. The important thing is that one can introduce a mass parameter that's would then preserve the supercharge that Princeton used for localization. So then we can imagine taking various derivatives with respect to these parameters. So for example, in order to get something supersymmetric, a supersymmetric 4-point function, we can take, well, we have to take 4 derivatives, and we have 3 parameters. So we can have various combinations of derivatives we can take. One example is we can take 4 derivatives with respect to the mass. So d4 by dm to the 4 log of z. Well, we can take a derivative of the log or derivative of z, doesn't matter, and then set m equals 0. That's one option. Another option would be to take 2 derivatives with respect to the mass, and then 1 derivative with respect to tau, 1 derivative with respect to tau bar. And then it's a convenient normalization to multiply this by the imaginary part of tau squared, but of course that's not necessary, they're just a normalization. And then set m to 0. So this would be another quantity that's an integrated correlation function. So these both would be examples of integrated correlators, 4-point correlators in n equal 4 supraimals that preserve the supercharged Q, and therefore therefore they can be computed using supersymmetric localization. Maybe I can make a note. Note. These integrated correlators, so these integrated correlators can be written as some integrals of the 4-point functions of the integrals of the 4-point functions of these operators Sij that I defined. I'm going to write this only schematically, but there are very explicit formulas for this. Sorry?
What are these cases?
There's S was phi I, Sij was trace phi I phi j minus 1/6 delta ij phi k phi k. So it's not a simple calculation, but one can show that if we consider these derivatives of the S4 partition function with respect to mass and respect to tau and tau bar, at the end of the day, we can rewrite it as some integrals of these correlation functions of these trace phi I phi j type operators. And they're very explicit formulas for what these expressions are. But I'm not going to go in that direction because I wanted to show you what the answer looks like for the integrated correlators. So for that, I just have to explain what the matrix model is when we include the mass, because that's the only new parameter we're going to have to include. So what is Z with mass and depends on tau and tau bar? Well, we started off with a Gaussian matrix model. So the Gaussian matrix model was the partition function for the Gaussian matrix model is, so this is just an integral over traceless Hermitian matrices. e to the minus 8 pi squared over g angno squared trace m squared. One can diagonalize the matrix M. So if we diagonalize it, it's going to be M is going to go to a diagonal matrix, and let's call the eigenvalues A. So A1, A2 through AN. For SUN, if we were to consider UN, then they would be independent. If it's SUN, they have to add up to 0. So then this Gaussian matrix model can be written just in terms of the A's. And the expression is this. So up to a factor, this can be written as an integral over the A's. Then there's a Jacobian from changing variables from the entries of the matrix M to the eigenvalues. And the Jacobian is a product, is a van der Waals determinant. It's a product of AI minus AJ quantity squared. And then there's e to the minus 8 pi squared over g angno squared. And trace M squared is going to be a sum over the AI squared. Sorry?
That's the orthogonal lump sum when you have.
This is unitary. Sorry, the.
Because you have that particular power dependent.
That's right. Yes. Yeah. If this were an orthogonal matrix or something else, it would be different. Okay. So the way I'm going to describe what happens when we have a mass, I'm going to describe that as a modification of this model by an insertion of an operator that depends on the mass. So in general, so I'm going to define the expectation value of some function of the A's in the Gaussian matrix model. This is defined as 1 over the partition function times the same expression, product I smaller than j, AI minus AJ squared, e to the minus 8 pi squared over g angno squared, sum of AI squared, times f of a. So with this definition, I can write down what the partition function is when we introduce a mass. And then we can take derivatives with respect to it and then compute it and expand it at large n and large lambda. That's the plan. So z plus 4 of m tau tau bar is an expectation value in the Gaussian matrix model that comes, one part of it comes from this one loop determinant in the localization computation. I'm going to call that the perturbative part. So they're going to depend on m and AI minus AJ. And then there's going to be instanton contributions from the poles. Those are going to depend on m, tau, AI minus AJ. It comes absolute value squared. This would be an expectation value in the Gaussian matrix model. I didn't do anything. I just have to tell you what the ingredients are. So first, let me tell you what the perturbative piece is. So z pert of m, well, okay, it's a function of m and AI minus AJ. It's a product from ij from 1 to n, some function h of AI minus AJ divided by the same function h, AI minus AJ plus m. That's where it's evaluated in the denominator. So what is the function h? The function h, so h of m is this. E to the minus 1 plus gamma, gamma is the Euler constant, times m squared, times a function g of 1 plus im, times the function g at 1 minus im. That's called the Barnes-G function. And we're already in business because Mathematica knows what the Barnes-G function is. So G is the Barnes-G function. It's also called the double gamma function. For all intents and purposes, Mathematica knows what it is.
Ratio of ages can be interpreted as
actually, if we write it in terms of the numerator comes from some of the multiplets from a vector multiplet in n equal 2 language, and the denominator from hypermultiplet. So it comes from different multiplets. Each of them is a ratio of fermionic and bosonic. So Barnes G, it obeys the equation. The reason why it's a double gamma function, it obeys the equation G of Z plus 1. It's gamma of Z times G of Z. So it's like a recursion formula like the gamma function, but with gammas instead of numbers. So it's like a double factorial type of thing. The instanton contribution, I'm not going to describe because it's not going to be important in the limit that we're going to consider. So Z instanton of M tau AI minus AJ is much more complicated, but it's 1 plus order e to the minus 8 pi squared over g angle squared at small g angles. So we can ignore it if we take n to infinity first while keeping lambda fixed, and then take lambda to infinity, because when we take n to infinity and keep lambda fixed, then g angles go to 0. So we can, but it's understood. It's understood what it is. It's much more complicated than that expression over there. So dropping instantons. Then one can then take two derivatives. Let's just take the mass derivative first of log z s4. Taking the derivative of z or taking the derivative of log, the difference between that is that when we take the derivative of log, we no longer have the disconnected contribution. That's the only difference. So from that point of view, taking the derivative of log is better because we get rid of the disconnected contribution. So this evaluated when m equals 0, this is the expectation value of the second derivative of this perturbative part, AI minus AJ, in the Gaussian matrix model. And now, well, if you stare long enough at these functions and you start taking derivatives, well, you're going to get some polygamma functions, and then we can think about how to deal with those. And the most convenient way of dealing with those functions, as is with many other operators that you could possibly think of inserting in a Gaussian matrix model, is to do a Fourier transform. So this can be written as some, wondering if I have enough room here, integral sum over INJ, integral over some parameter omega, which is there's a frequency in the Fourier transform of 2 omega over sinh squared of omega times the expectation value of e to the 2I omega AI minus AJ. The expectation value of that in the Gaussian matrix model minus 1. So that's the expression. So all we have to do in order to evaluate this derivative is to figure out how to compute an expectation value of an exponential in a Gaussian matrix model. Have we seen an expectation value of an exponential in a Gaussian matrix model before? Yes, where? The Wilson loop was exactly something, the expectation value of an exponential. So the way the Wilson loop is evaluated is the same way that this will be evaluated as well. There are systematic ways of evaluating it. But maybe it would be better to not. I can show people, whoever is interested, I can show you how to do that. But let me just write down the answer. The answer really to leading order, one can figure out what the answer is from there's the answer for the Wilson loop. So the Wilson loop at leading order went like there was a Bessel I function of square root of lambda. That's what the circular Wilson loop was. And here, because we have e to the 2i ai minus aj, we're going to have that squared, but analytically continued to imaginary values. So it's going to be a different kind of Bessel function. It's not going to be a Bessel I, it's going to be a Bessel j. So the answer is this. So log of the S4 partition function is at leading order is minus n squared integral omega 2 omega over sinh squared of omega times 4 pi squared over omega squared lambda Bessel j square root of lambda omega over pi quantity squared minus 1. So this is the analog. So this is the analog of expectation value of Wilson loop is approximately twice times I1 of square root of lambda divided by square root of lambda. It's a leading order in large n expression, but all orders in lambda. Now the integrated correlator was a little slightly different. It had two more derivatives. So if we define it, so let's just call it I, and it's imaginary part of tau squared times two derivatives, one with respect to tau, one with respect to tau bar, two with respect to mass of log z. Well, we can then act with these derivatives on this expression and get approximately n squared integral. The integral is from 0 to infinity integral in omega. Omega over sinh squared of omega. And the answer is Bessel J1 of square root of lambda omega over pi quantity squared minus Bessel J2. There's some identities of Bessel functions. Square root of lambda omega over pi quantity squared. So these computations, lots of special functions, lots of identities. One has to know both special functions and identities. Good. So this is leading at large n, but all orders in lambda. So if it's all orders in lambda, we can expand it at large lambda and see what we get. If we consider this limit, large n at fixed lambda, the instantons drop out because G angles goes to 0 and the instantons are suppressed, are exponentially small in that limit. If we consider other limits, and there are good reasons for considering other limits, for example, consider G angles fixed and then take n to infinity, then we would have to keep track of the instantons as well. So expand at large lambda, and we can get the integrated correlator is n squared approximately, it's large n. And then we have 1/4 minus 3 zeta of 3 divided by lambda to the 3/2 plus 45 zeta of 5 divided by lambda to the 5/2. So one can see exactly the powers that we expect from the large lambda expansion appearing. One can, of course, do it to subleading orders as well. So the next order would be n to the 0, and then the first term would be something like square root of lambda. It's minus square root of lambda over 16. and so on. Higher order terms. One can go, one can in principle do it. There's a procedure for doing it order by order in 1 over n squared, and at each order have an expression that's correct to all orders in Lambda. So are there any questions? Yeah. No, so this is going to give an integrated correlator on S4, but that's also because correlators on S4 are related to correlators on R4. This would also be an integrated correlator on R4. Yeah, that's well defined. Well, one has to, well, it's going to be the integrated correlator with an appropriate measure on R4 such that the integral is convergent. Yeah.
In a QFT with multiple supercharges, do these statements about Q invariance only have to hold in order to use supersymmetric localization? Do statements about Q invariance only have to hold for one?
For one, yeah, only need one.
M in this example could be any one of the 6 phi's. It doesn't have to be phi 6, right? Because there's a
the capital M, you mean? Yeah, because of the, that's right. That's correct. Okay. So, you know, this is maybe I can just tell you in the last 5 minutes, just tell you some lessons one can learn from this. You know, it's great. We managed to reproduce some expectation that about higher derivative interactions that we had on the from the gravity side. So just to remind you, so this here corresponds to a contact interaction with a Riemann to the 4 vertex. This one corresponds to a contact interaction with a d to the 4 r to the 4 vertex, and so on. So in some sense, this computation well, sort of validates predictions that we could have made just based on the form of the 10-dimensional action, supergravity, and corrections to it. So it validates the form of those higher derivative corrections. So lessons or other things. I'll try to be brief. So this is just the beginning of a series of computations that one can then do. So one thing one can do is to use this data from supersymmetric localization. So what we computed was an integrated correlator that in principle we had an expression for it in terms of a matrix model that holds at any n at any G-Yang mels. So one can try to use this and combine it with other methods. For example, it can be combined with bootstrap, both analytic and numeric. And one thing that's very powerful is that combining it with some analytic bootstrap arguments, just with that, so I can just draw an arrow here. Combining this with analytic bootstrap argument, one can derive this SSSS 4-point function. So this can be fully derived, not just integrated, but at separated points as well, at low orders in 1 over n and 1 over lambda. So, for example, even though the interaction vertices, the Riemann to the 4 interaction vertices are not completely known, and we couldn't compute the contributions they make to this 4-point function at separated points, nevertheless, analytic bootstrap arguments combined with this can give us what the contributions of those Riemann to the 4 vertices to this 4-point function are. For example, at order n squared, so same order that we're looking over there, we can fully determine lambda to the 0, lambda to the -3/2, lambda to the -5/2, completely at separated points. One thing that I did not mention is that CFT correlation functions computed using ADS-CFT are related to scattering amplitudes in flat space. So one can take a flat space limit of ADS space, so taking the radius of ADS to infinity, and then we just get flat space scattering amplitude of gravitons and their superpartners in 10-dimensional flat space. So a picture to have in mind is that if we have ADS space and we think of it like a box like this, we can create some wave packets. The wave packets interact somewhere here, and then they go back to the boundary. So this is what the CFT correlator. We can engineer something like this from a CFT correlator, and then if we take the limit where the radius of ADS goes to infinity, say in string units, that's the same thing as taking n to infinity, we can get a scattering process in flat space. And Joao taught us precisely what to do to the CFT correlator in order to reproduce the scattering amplitude in flat space. Using analytic bootstrap as well as the supersymmetric localization results, we can determine that CFT correlation function at arbitrary points, and then we can pass it through this flat space limit and determine scattering amplitudes in flat space. And those scattering amplitudes in flat space had been computed using string worldsheet methods, and there's agreement. So this is a highly non-trivial test of ADS-CFT that goes beyond the supergravity approximation. It would be higher derivatives. One can take more general limits. One, as I said, one can keep G-Yang mills fixed as we take n to infinity. That's also very interesting. One finds some Eisenstein series in that case that were also seen in scattering of strings in flat space. And well, a broader comment is that, well, with calculations like this, like CFT, ADS-CFT, n equal 4 super Yang mills, can teach us quantitative lessons about quantum gravity or string theory. So studying gauge theories may not be good only for studying confinement. I understand that's the purpose of the school, but also for studying quantum gravity. And yeah, if we combine these methods with bootstrap and eventually as a dream manage to solve n equal 4 super Yang mills, we can then use it we can then deform it, and then that would help us solve other theories. I mean, just as a matter of principle, it's not entirely obvious that if we want to study QCD in the real world, the best starting point should be the lattice regularization of QCD or whatever, weakly coupled. QCD is strong in the infrared, strongly coupled. It's not obvious that one should start with a weakly coupled theory. Maybe an equally good starting point would be some other strongly coupled theory that can then be deformed to QCD. So anyway, thank you very much.
So if we consider the exact computation for finite n, there's an error term coming from the certain partition function. So this is non-positive in 1 over n. So how do we understand it from it is 5 times this?
So you're talking about the instanton contribution or no?
This O of exponential.
Yeah, that's non-perturbative in G Yang. It's very small. It's small G Yang mills, and that corresponds to yeah D0 instantons.
Can we also match this term from gravity side?
Yes, there are some checks one can do. So we can work. Yeah, that can be matched. So through this more complicated procedure, with also with the flat space limit, it can be matched to string worldsheet computations. That instanton contribution. Yes.
Is there any way to think about the meaning of symmetric localization in bulk?
Well, that's a very interesting question. I don't know the answer. I mean, one can speculate that you know, this is a matrix. We did localization in the CFT. We obtained a matrix model. So if we were to do localization in the bulk, maybe we obtain the dual of the matrix model. But I don't know what that is. It would be very interesting to figure it out.
Any further questions? Silviu again.